Hello everyone, my name is Jim Corkins, and we're going to go ahead and begin Physics 112 and Physics 131 with this first part called Introduction to Charges. And then later on we're going to lead into what is the Coulomb's force, and then one-dimensional forces, and then two-dimensional forces. Okay? For this first part we're going to just we're just going to go through what are electric charges and how do they affect each other and how do they give rise to a force later on. Okay, so if you haven't done the reading, please do so. It'll be in chapter 17 in Coletta. If you're in Physics 112, it'll be OpenStax chapter 18. And if you're in Physics 131, it'll be OpenStax volume 2 chapter 7. Okay. And try to begin your homework if you can. It'll be homework 1 and homework 2, which is related to this chapter. Okay? All right. So, like I said, what we're going to be doing is we're going to be going through what are electric charges. And to start that, we're going to talk about what the charge model is and then what is a charge. We're going to talk about insulators and conductors. And then we're going to talk about Coulomb's law. And then we're going to try to apply Coulomb's law in 1 and 2 dimensions, and also integrate that force. So it'll be force diagrams. We're going to integrate those force diagrams with what you learned in Physics 121 and Physics 111. Okay. So we've all seen a thunderstorm, and really they're amazing, and it's just very profound in how little it makes us feel. So you can really feel the power of the earth during those times of really, really thick thunderstorms where they have lightning and thunder and everything. And usually you'll see that right around monsoon season in July and August. Okay, sometimes into September too. So what is really going on which causes basically a lightning to fly out of the sky, right? Well, we're going to kind of investigate that a little bit. So to do that, we're going to actually talk about what is the fundamental interactions of electricity, and from that, what is electric charge, and once we go through that, we're going to talk about the electric forces, and then we're going to talk about electric fields in the next chapter. Okay. So to begin talking about this, we first need to talk about atoms and electricity. So a lot of you have already taken your chemistry courses, so you probably have a lot of experience with this. But for those of us who haven't, and even for you who already have, let's do a quick review. So here we have an atom, okay, and inside that atom, at the center of the atom, is the nucleus, okay? And on the outside here in the valence bonds, these are where the electrons are found. And these are little, and we're not really going to be talking about electrons in orbiting as a way a planet orbits a star, really. But this is more of like an electron. It's more like a cloud, really. It's hard to know. You can't really know the position and also the speed of an electron at the same time. So, but inside the nucleus now, excuse me, there are protons and neutrons stuck together. Okay, so that's what makes up a nucleus. All right. So what is holding this atom together is an attractive force between the positive nucleus and the negative electrons. Right. So that's what's these positively charged protons are actually attracted to these negatively charged electrons. Okay, so these electrons are being held here together by these protons. So in order for them to remain together, they have to be attracted to each other. Okay, so the fundamental unit of charge for both protons and electrons is the symbol, is the E symbol, okay? And I'm going to mark up this document, and if you've never marked up an Acrobat Reader document, what you do is you go here to the Comments tool, okay? And when you highlight it here on the right hand side, you'll see like a little window. It looks like a little TV screen. You click it, and then that pops out this window right here. Now you'll notice when you do that, all these tools come up. Okay, so I'm going to push this back into place, and now we have all these tools, and we have our full screen. So I'm going to, in these tools you have a pencil. If you click on the pencil, you could change the color to different colors. Here you have an eraser. You could erase your drawings. And you could, over here are are little shapes that you can insert. You can insert vectors, lines, rectangles, ovals, things like that. You could also put in place a text box. And if you click that text box, then you'll have options to subscript and superscript things too. And you could actually change the color of that text box. Okay? But right now, I'm going to just be using a pencil. Okay? And so this fundamental charge of a proton and an electron, okay, typically we use actually a Q. Okay, an electron would be an E, a proton would be a P, but typically both charges have an overall magnitude charge of 1.602 times 10 to the negative 19th coulombs. So it's a really, really small number. And this chart, this is a unit called a coulomb. Okay? Called a coulomb. Alright, so that's the unit of charge, capital C, which is called a coulomb. Okay? Now, if it's a proton, it will have a plus in front of this number. It'll be a positive 1.602 times 10 to the negative 19th coulombs. And if it's an electron, it'll have a minus 1.602 times 10 to the negative 19th coulombs. Anytime we put a Q in an equation, which is the charge of a proton or an electron, okay, then that is called a test charge. All right? So the mass of a proton is actually very, very massive in comparison to an electron. Okay, so protons and neutrons are really massive. They're both 1.67 times 10 to the negative 27th kilograms. And 10 to the negative 27th kilograms is a point. And then you have, well, 0.0. And then you have 27 zeros. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and then 27 would be that, 1,673 kilograms. So a proton is a super small mass, and a neutron is about the same mass. It's just a little bit larger. But electrons are much smaller than that. In fact, they're 10 to the negative 31st. And if you think about that, I would have to add more zeros here. So this is a proton's mass. An electron's mass would be to the 31st, and that's 9,109 kilograms. And here we have, this is going to be 10 to the 27th, so I've got to add a couple zeros. I've got to add 6 zeros here. 1, 2, 3, 4, 5, 6. So the electron is much smaller, much smaller. In fact, it is 10 to the 6th smaller. Then 10 to the 6th smaller is 1, 2, 3, 4, 5, 6. Okay, so it's got 6 zeros in front of it, smaller than a proton. So it would be kind of like comparing the weight of you to the weight of a couple of school buses. Okay? So if you put like 5, 6 school buses together, that's about how much weight difference it is between a proton and an electron. In fact, I think I'm a little bit low on that. If you weighed 1 kilogram, whatever the object would weigh would be 1, 2, 3, 4, 5, 6, 7 would weigh 1 million kilograms. Okay? And a kilogram is 2.2 pounds. So if you weighed 2.2 pounds, this would be 2,200,000 pounds. That's kind of the difference between an electron and a proton. So much, much heavier. A proton is much, much heavier than an electron. Okay? So now that we know the charge of an electron and the charge of the proton, again, those would just be plus or minus. Proton is plus, electron is minus 1.602 times 10 to the negative 19th coulombs. Okay, now we could talk about atoms, all right? So we've talked about what makes up atoms, protons, neutrons, and electrons. So in the nucleus, okay, within a lithium nucleus, you have 3 protons, you have 4 neutrons, and you have 3 electrons, right? If it's a balanced atom, the number of protons is going to be equal to the number of electrons, and the number of protons is going to be equal to the number of neutrons plus 1. Okay? Okay? And if it's balanced, the number of protons is going to be equal to the number of electrons. I'll put little pluses and zeros on these to keep that in place, right? So if you have a nice balanced lithium atom, there should be 3 protons, 3 electrons, and 4 neutrons, okay? But what happens, and this happens a lot, when a lithium atom will lose one of its electrons? Well, its charge, you have 3 protons, 3 electrons, so you have 3 positives and 3 negatives. Well, that adds up to 0 charge, right? Well, now you've lost a negative, okay? And now that means this atom, this lithium atom, is now positive by 1 proton. Okay, it's now got an overall net charge of positive 1.602 times 10 to the negative 19th coulombs, right? So this has got 1 extra proton than an electron, okay? So it's in a state of imbalance, and this is also called a positive lithium ion, okay? So a positive lithium ion can have, basically what that's saying is it has more protons than electrons, okay? And the counterpart to that is what happens if the lithium ion is neutral, again, and it gains an electron. Well, now it's got an overall negative charge to it. So its charge is now going to be negative by 1.602 times 10 to the negative 19th coulombs. Okay? And I want to point out, too, that only electrons come off an atom and go back onto an atom, right? Protons will not leave the nucleus. They'll, for the sakes of our learning for right now, we're not getting into atomic physics or nuclear physics. So we're just going to be dealing with a stable nucleus where the protons don't leave or anything like that, and you're not splitting the nucleus, okay? So electrons really are the things that are leaving the nucleus, leaving the atom or jumping onto the atom. The protons and neutrons are staying right in place. Okay, so that's the big takeaway from this. So how do you, so now that we've got some of this information together, let's go ahead and put it together in one table. So we talked about how a proton is positive 1.602 times 10 to the negative 19th coulombs. and its mass is 1.673 times 10 to the negative 27th kilograms. We also talked about an electron having the same magnitude charge, but being negative. And this is, again, the unit of charge is called a coulomb. And that should be a capital C. Anyways, and its mass is 9.109 times 10 to the negative 31st kilograms. All right? So if you want to figure out the overall net charge on an object, okay, what you do is you take the total number of charges, so this is the net charge on an object, which is going to be Q. You take the total number of charges, either positive or negative, and you multiply it by the magnitude of a charge, which is 1.602 times 10 to the negative 19th coulombs. Okay, and so if you added a proton to this, so it would be one proton, so now the overall net charge would be 1.602 times 10 to the negative 19th coulombs. If you had two protons, if you had an object, if you had an atom that lost 2 electrons, well, now it's going to be positive by 2 protons, and now it's going to be 2 times 1.602 times 10 to the negative 19th coulombs, and it'll be a positive 2. All right? So you'll use this, you're going to use this to figure out the total numbers of charges on it, right? So if something had a charge of 1 nanocoulomb, so let's say an object had a total charge of 1 nanocoulomb, which is 1.00 times 10 to the negative 19 to 10 to the negative 9. A nano is 10 to the negative 9 coulombs. Well, you'd go, okay, and let's say it had an overall positive charge on it. Well, you take the number of charges, multiply it by 1.602 times 10 to the negative 19th coulombs, and now to figure out the total number of protons that is here, you divide this by 1.6 times 10, 1.602 times 10 to the negative 19th coulombs. And that would get you the total number of protons built up on this object. Okay? Which would be 1 divided by 1.602. So 1 divided by 1 divided by 1.602 is going to be 0.62. This would be 0.62. Let's make sure that's correct. I don't have to round or anything. Times 10, and this is negative 9. You bring this 10 to the negative 19th up, it'll be negative 9 times 10 to the positive 19th, because that's now on top. And so that total number is going to be 0.602 times 10 to the 10th charges. So it would have, what is it? 602, and so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it would have 6 billion, 20 million, 6 billion, 20 million protons built up on this object. Okay, so this is how you use total charge of an object to figure out the total number of protons given a single charge. So you basically divide the total charge on the object by the charge by a single charge, okay, and that tells you the total number of charges built up on that object. And make sure to include your negative and positive on this, okay? And so I was assuming that this total charge is going to be positive, and so this is going to be a positive 1.602 times 10 to the negative 19th coulombs, and that way the number works out to be a positive number, and that tells you that those are protons and not electrons, okay? So that's how you figure out the total number of charges on an object, They give you the total number of charges, the total charge of the object, and you divide it by a single charge, and that tells you the total number of charges built on that object. So now let's talk about insulators and conductors, and what are the differences between them, okay? So first of all, what is an insulator, okay? And so if you've ever worked with electronics or anything like that, you've seen little copper wires, and they have rubber or something kind of bound around the wire, or they might have plastic or things like that, right? Well, that copper wire is going to be the conductor, and the rubber is going to be an insulator. Okay, so typically insulators are kind of rubber or plastic, and really what an insulator is the electrons of an insulator. Okay, so whatever the substance is of the substance is of this insulator, it's made up of atoms, just like conductors are. However, these atoms are made of a compound where the electrons basically are not free to jump from their place. Basically, the electrons will stay localized to this area. Okay, if you have a conductor, they could go to different objects. Okay, so what I mean by that is if you had a sphere, okay, of, let's say, a plastic sphere, and you added little electrons at this point right here, so you put a bunch of little electrons at this point, okay, so you added electrons. Well, a few minutes later, these electrons will still be right where you added them. Okay, they'll stay right where you added them. Okay, so if conversely, if you so you could add. We'll talk about how you add charge or take away charge from an object, but conversely, the cool thing is too is you could actually rub an object on a neutral object and then tear away the electrons from this patch right here, and so now there's going to be just positives here because you've torn away the electrons, and now it's not neutral anymore. So now electrons are surrounding this area, and they want to go to this area, they want to go to this patch and fill in these holes, but they can't because these electrons are also stuck where they are on this insulator. Okay? So basically what an insulator is, it's a substance, so it's made of a compound, where the electrons really can't leave their location. They're kind of stuck where they are. So if you add electrons to this place, they're going to stay right there. If you take away electrons from a place, the electrons surrounding this aren't going to jump in and fill those holes. They're going to stay basically where they are. And this will be a patch of positive on this object. That's an insulator. Okay? Conversely, a conductor, the electrons will actually, they're loosely bound or weakly bound, electrons are weakly bound to the nuclei. So the electrons here will actually very easily hop from one object to another. Okay? So the electrons can essentially drift from one side of the object to the other side of the object. Okay? And what will cause it drifting is whether it's attracted to, let's say there's a proton over here that's all by its lonesome. You put a little proton over here, and he has no, or he or she has no electrons. Well, and if you have a loosely bound electron, it's going to immediately see this guy and try to bind with it. All right? Because they could just go wherever they want. So the electrons are just kind of buzzing around here all the time, and they'll go to the other side of the object or stay right where they are. And so a similar example that we just did, if you inject electrons right here, so you add a bunch of Q's, so you're adding Q's right here, what's going to happen on a conductor are these Q's are now going to be repelling each other. So they're going to try to get away from each other as far as they possibly can. And by doing that, a few minutes later, they're going to go ahead and they're going to be, they take on actually a form of a structure when they do that, because they want to be equidistant from each other. They want to keep all the other electrons away from them because they're repelling from them. Okay? And the other example that we said, if you had a little patch here and you ripped electrons away, so just like this object, you tore electrons away, well, these electrons in the insulator are going to stay right where they are. However, if you did this, if you ripped electrons out of here, and you tore electrons away from that area, okay, well, all of these electrons, which are now free to move, are going to jump in there and try to balance it out. And so now, eventually what would happen is this object would become neutral again. Okay. So overall, right in this patch, it's now positive, but then eventually these electrons are going to fill that gap and pair up with those protons. Okay, in that area. And they could come from one side of the body or the other. So with conductors, electrons are free to roam all over the entire object. But with insulators, electrons are kind of stuck in their place. And that's because their valence bonds are really tightly bound due to the type of substance it is. And they take the substances, compounds, they have a structure to them, and sometimes it's actually just the substance itself, but also it's actually how the substance is organized that actually can cause this to happen too. Okay? So that's basically the difference between insulators and conductors. And so here's some better slides to describe what is happening. So if you take a negatively charged rod, and we'll talk about how you can make an object become negative or positive. We'll talk about that a little bit. It's called charging an object. So if you take an object that has an excess of electrons on it, and you bring it here close to a conductor, it's going to dump those electrons here. It's dumping exactly 5 electrons onto this conductor. Immediately, these electrons are going to space out as far apart as they can if it's a conductor. However, if it's an insulator, where you dump those electrons, they're going to stay right there. Okay. So at time 1, with an insulator, you're going to put those electrons right there. At time 2, they're not going to space out. They're actually going to be right where you left them. Okay. But with conductor, if you dump 5 electrons right there, another moment later, they're going to immediately spread out as far away from each other as they possibly can. Okay. So how do you charge an object? Okay. So you've been in grade school and you've probably done little experiments, right? Or if you have had an older brother like I've had, and at one point in time you've been sitting on the couch minding your own business, and your brother, who thinks they have superpowers, rubs their little feet against the floor, the carpet, and they're in their little onesie, and the bottom of their feet are these smooth kind of plastic pads. Well, they rub it against the rough carpet, and the worst is if you have new carpet, right? They just kind of zap you, right? So what is happening here in your 3rd grade classroom too is the same kind of thing. Here you rub this object, which is we'll just say it's a piece of amber or a piece of glass with silk, and you rub it against your hair, okay, or a piece of fur, for example. This looks like a toupee. Please don't take off your toupee and rub it against a piece of amber. That's weird. But anyways, you rub this amber rod against your hair, and then you notice that these little pieces of paper will now stick to it, right? But when you didn't rub it against it, they would just not even notice each other. So what is kind of happening? So what have you done in both situations where you rub this amber rod with a piece of fur, and now it's actually able to pick up objects, little pieces of paper, And also, how is it that your brother who rubs his feet against the floor is able to shock you? So that is called charging, and it's also called charging by friction. Okay? So all of us have done this too, probably in science class, where you rub a balloon against your hair. Okay? You rub a balloon, so you take a balloon by itself, you blow it up, and you put it against a wall, it will just fall down. But if you rub this balloon against your hair, well, now it'll stick to the wall. So what is happening to do this? Okay, well, let me pull up this simulation. So this is a PHET simulation, and I'm going to show you what's going on. So here I am at PHET, and all I did is I typed in PHET in physics in the search window, and this came up, and I clicked on it. Okay, so now I'm going to go to simulations. And I'm going to just hover over simulations and click on physics. All right. And then when I'm here, actually the balloon static electricity comes up right away, but I want to show you how to get to it if it doesn't come up. So you would go in physics, you'd go to electricity, magnets, and circuits. Okay. And then from here, they're actually putting it right here. And you look for balloons and static electricity. All right, and this is run in HTML5, so it should work on Macs as well as PC. And you hit run. You hit that little run button, and it basically starts up your simulation. So the balloon doesn't stick to the wall normally. You just put it against this wall, and it'll just fall right back down. Okay, it won't stick at all. And that's because before you do any charging by friction, everything is neutral. Okay, and what I mean by that, everything is balanced. For every proton, there's an electron. Okay, if you notice this shirt, which is supposed to take the place of hair, it's a wool shirt. You have rubber, and you have a neutral wall. Okay, so everything is neutral, and if objects are neutral, really, they don't really affect each other. Okay, so what's going to happen here is something really interesting is going to happen. Now, I want you to try to see if you could induce the rule from this. Okay, so notice the locations of the protons and notice the locations of electrons, and notice the protons and electrons over here. When I rub this balloon against this wool, look at which charge do you think I'm going to gather, the protons or the electrons? Okay. All right, and I want you to think about that for a second, because remember how we were talking about before that electrons exist in a cloud around the nucleus, and that the nucleus is really strong, and you're basically not going to dislodge protons from their place in the nucleus. Okay, so if we're right, the electrons are actually very easily ripped out of their orbits or their electron cloud from a nucleus, well, from an atom. Okay, so essentially, I expect that when I rub this balloon against here, either the balloon is going to give electrons to the shirt, and this will be positive, or the balloon is going to pick up excess electrons from the shirt. But what we can say about this for sure is that it's only the electrons that move. The protons do not move between objects. Okay, they stay right where they are. So I'm going to go ahead and rub this balloon against the shirt, and look at what I'm doing. I've gathered up electrons. And now I've gathered up all the electrons on the shirt. It's impossible to do that, but let's just, for the sake, there's not that many electrons on the shirt. There's an incalculable number of electrons on the shirt. But here we go. You have all the electrons that are now gathered on this insulator. Okay, so notice the place where I rubbed it is where the electrons are now gathered to. Okay, and so now those electrons, since it's an insulator, are stuck on this side. Well, now what do you think is going to happen when I bring, well, if I let it go right here, notice the electrons are trying to get back to this shirt, right? But since I've gathered them on this insulator, they're not able to jump off onto the shirt. They're now stuck on this balloon. Okay, and notice when I let it go, it then is now attracted, and it wants to stick to this shirt because the electrons are trying to jump back onto these protons. Well, now if I bring it over here to this neutral wall, what do you think is going to happen? Do you think the balloon is going to again hit the wall and fall to the ground? And remember, this balloon is now a net negative charge. So what do you think is going to happen? Well, if I let it go right here, it's now stuck to the wall. Okay, and notice one other thing too. The electrons in this wall are now moved away, right? If I bring, they're now right where they normally are, but when I bring them closer and closer and closer, it seems like they're being repelled away, and they're actually being repelled away from these electrons. Okay, and since the wall is an insulator, and since the balloon is an insulator, the electrons aren't going to leave the wall, but really what's happening is they're leaning away, so that these large amounts of electrons are now closer to these protons. And since these electrons are now attracted to these protons, the balloon is able to stick to the wall. Okay, so basically these atoms are just restructuring themselves, so now the protons are close to these electrons, and these electrons are just kind of leaning away. Okay, so they're basically, nothing has changed. It's still a neutral wall, but these electrons are now leaning away and allowing these charges to be closer. All right, let me redo that again. I'm going to try to rub it again, and just notice that these guys again are still leaning away. However, if I reset everything, and even though these guys have electrons on them, now they're both neutral. And since this is overall a neutral object, it's not going to affect the overall structure of these neutral atoms. They're going to just almost not notice each other. Okay? So that is what is happening when you charge an object. When you charge an object, you're gathering or giving up electrons, right? So when I take this neutral balloon, I'm gathering up negatives on this balloon. I've charged this balloon as negative. But the interesting thing is, this wool shirt has also been charged. And really, that's a weird term to say because it's actually lost electrons. But now it's got a net charge of positive, and the balloon now has an excessive charge of negatives. So by charging this balloon with negatives, you're basically taking electrons onto this. But by doing that, you've actually charged this wool shirt with taking its electrons, and now it's positive. And this wool shirt would, if I could grab it, it would be able to stick to the wall too. So you could put the balloon against the wall and the wool shirt against the wall, and they would both stick. Okay, and where the wool shirt would stick is where the electrons would actually be leaning towards this. So the electrons here would actually gather, these electrons would actually gather right here if you brought the wool shirt over here. So that's called charging by friction. And charging by friction essentially is where you're taking electrons, and again, it's only the electrons that are moving. You're either taking electrons from an object, or an object is giving its electrons onto another object. In either case, you're charging it, either charging it positive or charging it negative. Okay? And so that's essentially what we're going to be doing, is charging objects by friction. Okay? And again, it's the electrons that move. So rule number one is electrons move, protons stay where they are. Protons stay where they are. Okay? And it looks like that electrons will be attracted to a neutral object. Okay. And let me do it this way. An electron will be attracted to a neutral object, and that's because the proton will restructure, the atom will restructure itself so that the atom's electron is further away from the electron and the proton is closer to the charged object that's negative. And the opposite is true. If you have a positive, if you had that wool shirt which was positive and brought it to the wall, you would see the electron in that wall try to get closer to that wool shirt, and the proton would move away. So if you have a charged object, whether it's charged negative or charged positive, they will be attracted to a neutral object, but also really what's happening is they're being charged with the oppositely charged object, oppositely charged charge, since the atom is restructuring itself. Okay? So we're going to get into modeling charges, moving on to other modeling charges, moving on and off objects, and also then the results of that, where you then put it up against an object and it'll be attracted or attracted to or repelled away from an oppositely charged object. Okay? So the first thing that we learned is that we talked about how frictional forces will rub and take off electrons from one object and put it onto another object. And so this is actually called charging an object by friction. Okay? And then now, I want to point out there are two kinds of charge, a positive and a negative. So when you do this, when you charge by friction, you're either taking electrons off an object, and now that new object is going to be negative, and that other object is going to be positive, or you're putting electrons onto another object. Okay? And just so you know, if we haven't really talked about it, like charges will repel. Okay, so a positive will repel another positive, and a negative will repel another negative. Okay, and so these forces, if you noticed in our simulation, right here, if you pay attention, see these electrons, even though this object's really far away, they actually start to react. See them kind of moving and jiggling? So this Coulomb force, this repulsive or attractive force, exists over a very, very large distance. Okay? And neutral objects are balanced. They have both positives and negatives, and they will react by restructuring themselves so the positive is closer to the negatively charged object, while its negative on that atom is going to lean away, and so it's further from that charged object. Okay, and by rubbing, you're going to be transferring electrons from one object to another. Okay, and again, electrons don't disappear, so this is called conservation of charge. Okay, electrons, charges, positives and negatives, and neutrons for that matter, aren't created or destroyed. They basically just change places, right? And what we had saw is that all the electrons that were gathered from that wool object got transferred to the balloon. Okay, none of them disappeared. So you have to be a good accountant when you're doing this. When you're trying to follow a problem and look at the relation and make sure you do good accounting and account for all the electrons that are ebbing and flowing from one object to another. Okay. Also, good thing to remember is that there are conductors and insulators. Conductors, when you drop a charge in a place, those charges are going to move all over that conductor and try to get as far away from each other as they can. If you dump charge on an insulator, a few seconds later, they'll still be where you dumped them. Okay, so insulators, the electrons don't move. Okay? So we're going to be applying these rules as we go through and do. So here's a brief overview of charge diagrams, right? So if you have an object that is neutral in charge, you're not going to account for, first of all, you're not going to account for all the positives and negatives on an actual object, right? Can you imagine just even a marble that's not that big? It has so many protons and electrons, you could not account for it, right? And not only that, you don't want to draw all your positives and negatives on this object, okay? Because it starts to get really busy and it's really hard to follow. So really, if you have an object that is just blank, we're going to assume that is a neutral charge. So both of these are neutral charges, but it's best to just note when a charge has an excess amount of charge, right? So if I took 2 electrons away from this neutral object, now this neutral object would be charged with 2 protons, okay? And so you would just draw those excess charges on here and assume everything else is neutral around it. Conversely, if this was a balloon that was neutral and I rubbed it very briefly against my hair and I gathered 2 electrons to it, well, now this overall guy is charged by 2 electrons. So it's much easier to see that than if I had added those 2 electrons here. Now I have to do a lot of counting. So positive, negative, that's neutral, positive, negative, that's neutral, positive, negative, that's neutral, positive, negative, neutral. Oh, I'm over by 2 electrons. It's just easier to see when you just assume everything else is neutral and just draw the excess charge, okay? So I'm going to remove those. And so here we have a conductor, and what they're saying here is you've taken a bunch of electrons away, and now those protons are spaced out here. And now you could easily be able to count this, and this would be a lot of counting to do, but you could do it, and it's very clear that this has an excess of protons on it, and that the electrons are missing. Here we have an insulator, and you've added electrons right in this area, and you can see now that it's neutral everywhere else, and now you have an excess number of electrons right in this area. So for clarity, we really are only noting the excess of charge on these charge models, and we don't really note positives and negatives. Although sometimes I'm just giving you advice, sometimes you might want to note these positives and negatives in some cases, but most of the time you don't. Another thing to keep in mind is that charge is conserved. So if you took electrons off of this object and dumped it onto here, if you took exactly 2 electrons from this object and dumped it onto here, you wouldn't have 2 electrons changing place and then only 1 end up here, right? So you have to remember that electrons and protons don't disappear, okay? That if you take electrons off one object, the exact number of electrons has to be put on another object, okay? And again, it's the electrons that are moving. So this object is positive not because you've added positives here, but because you've taken electrons away. And when you take electrons away from a neutral object, now it will become a net positive object. If you add electrons, like you did over here, to this neutral object, well, now those electrons have been added. So again, it's the electrons that move, the protons do not move, okay? So if you're going to be drawing this, you're going to try to draw it, if it's on an insulator, you're going to draw where the charges land. They're not going to move. And on a conductor, you're going to want to draw it so that those charges, those excess charges, are spread out, whether positives or negatives, okay? And again, on neutral objects, you don't put any charge in there. Just keep them like it doesn't show anything. And that way, it looks nice and clean, and you could assume that since you're not seeing any excess charge, that is a neutral object. Okay? So that's the brief of that. If you want a more detailed version, I think I put another detailed version in the notes. Okay. So again, charging by friction. If you have a plastic rod, a plastic, an amber rod rubbed with fur, or plastic rod rubbed with fur or wool, what's happening is this rough hair is being rubbed against, so they're both neutral right now, so there's no excess charge. And then when you start rubbing this rough object against this smooth amber, what happens is the rough object will give its electrons to the smoother object, okay? And since it's taken 2 electrons from the hair, now the amber's got it's got an extra 2 electrons, and it's taken those electrons from the hair. So the discrete steps are like this. You have 2 neutral objects who are initially neutral, so they're not going to be attracted or repelled to each other or anything else that is uncharged. Okay, so that for every positive, again, neutral means for every positive there's a negative, so they're electrically balanced. Okay, and that's what they're kind of showing here. And now, what you're going to go ahead and do is you're going to go ahead and start rubbing the wool, the neutrally charged wool, onto the neutrally charged plastic. And when you do that, you are going to start picking up excess electrons, because the plastic is smooth, the wool is rough, and you're going to be taking electrons from the wool, and now the wool that you've taken those electrons from is going to be positive, and now by 3, and the plastic is going to be negative by 3, just like with the amber and the fur. So what is really happening here is so now once you bring that charged object towards a neutrally charged object, so you bring that electron, or if you bring a positively charged object close to a neutral atom like this, so you bring a positively charged object close to a neutral wall, just like we did before in that balloon. What happens is the atom would look just normally like this, but when you bring the proton close to it, the atom doesn't gain electrons or lose electrons. What happens is it restructures itself, and the electrons will lean over. So it's the electrons that are going to lean towards this positively charged object, right? So just like in the wall, if you have a positively charged object, you bring it close to a wall, the atom is going to restructure itself so that the electrons are going to be as close to that external charge as possible, right? And so again, it's the electrons that are moving. In that one simulation, if I go back to it right here, if you notice, as I'm moving this, it's the electrons in the wall that are reacting and not the protons, okay? Protons are going to stay right basically in place where they are. Okay, it's going to be the electrons that are ebbing and flowing and reacting to a charged object. Okay, so that is what's kind of happened, and this is called dipole polarization. When you bring a charged object close to a neutral object, okay, neutral atom, those dipoles, and dipoles means for every positive there's a negative, so this has got a total of 3 dipoles. So dipole is a positive and negative. 2 poles, dipole. So this has got 3 dipoles. So those 3 electrons are going to restructure themselves to move closer to this charged object. Okay? So we talked a little bit about dumping electrons onto a conductor, or dumping electrons onto an insulator. Right? Again, with an insulator, if you put electrons onto an insulator, they're going to stay right where you left them, okay? But this is called transfer of charge, okay? So when you take a charged object, so you've taken amber and rubbed it against fur, or you've taken plastic and rubbed it against wool, okay? Now it's got an excess of charges. You've torn those electrons off of the wool, And now you're going to hold it close to, now what charge is this object right here, this metal object? Would you say it's positive, negative, or neutral? Well, it doesn't have anything in here, so you should assume that is neutral. Okay, so this metal is neutral. Well, now you're going to transfer these electrons on this neutral charge. So you're going to dump them right in this location. And you'll notice again, very quickly, those electrons are going to spread out and get as far away from each other as they can. And it's weird, if you limit how far an object can go, if you tell 20 people to get as far as away from each other as they can, and they're in a square room, they're going to actually structure themselves quite orderly because they have to be equidistant from each other. And they're going to be up against the walls and be highly structured. Okay? So, again, with a conductor, the electrons will transfer onto that conductor and then spread themselves around. Okay. Now, one of the cool things, this is called charging by induction. Okay. So if you had a positively charged object and you're neutrally charged, right? So again, this is another type of transfer of charges. Let's say you're neutral and you have a positively charged object. What is going to happen is you're going to send your electrons from your body. So you're going to send all of your electrons onto your body to pair up with all of these guys right here. And it looks like that you sent 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons to pair up, such that now you were neutral in the beginning, and now you are positively charged by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You are positive by 11, and this guy's only positive by 1. Okay, and now essentially, again, your electrons jumped onto this metal and paired up with all of these guys as much as they could, and only one guy didn't get paired up, and now you, which were neutral, you've lost those electrons, and now you're positive by 11. So this object in the beginning was positive by 11Q, and you were neutral, and now it's only positive by 1Q, and you are now positive by, this was positive by 12, I'm sorry, in the beginning. This is positive by 12Q in the beginning. And now you're positive by 11Q, and there's only 1Q that's unpaired. Okay? So those are two ways in which you're transferring charge. Again, it's the electrons that are moving on and off objects. In this case, the electrons are moving onto a metal object and distributing themselves. In this case, you have a neutral object and a positively charged metal. The 11 electrons are leaving your body and pairing up with all those positives, and now you're positive by Q, by 11Q. Okay? And we talked about dipole polarization, but there's also another case too, where there's this object that we have called an electroscope. Okay? And essentially it's a piece of metal with two pieces of aluminum foil. And these little charges, okay, if you bring this positive, so it's a neutrally charged object, and you have two pieces of aluminum foil that originally would be down. If this was neutral, you'd have this object right here, and the two pieces of aluminum foil would just be hanging down right here, and kind of looks like I drew a little bit of a person there, but this is those two pieces of aluminum foil that would be normally just hanging straight down, right? But if you bring a positively charged object up here, the electrons, which are normally just, in this case I'm going to draw the protons. So it's neutral. And then I'm going to draw the electrons. So it's got, for every proton there's electrons, so it's nice and neutral. Okay, nothing's going on. Now it's really beginning to look like a person. Anyways, so once you do that, what is going to happen is this neutrally charged object, when you bring this positive here, again, dipole polarization is going to happen, but this object is a metal object. So the electrons down here, all these little electrons that are all over the place here, are going to actually gather at the top. Okay, and I'm going to leave in my object, in this case for education purposes, I am using positives. The positives that I drew originally were right there, right here, right here, right here at the end. So they're going to stay where they are, but all these little electrons are going to now try to get up and close to this object, right? So they're all 1, 2, 3, 4, 5. 5 of these guys are going to now gather as close to this object as they can. Okay, and that's because of dipole polarization, but also because this is a conductor and the electrons can leave their valence bonds and travel to other parts of the object. And so here's, in the beginning it was like this, and then you brought the positively charged object close to it, and now all those electrons that were bound here are going to move up to the top here. And how we draw it is also those 5 protons would be down here. So we're just kind of representing it. I actually like just drawing the electrons reacting and leaving the protons where they are. But the protons would actually stay where they are, but they would just kind of lean away. Okay, it's the electrons that are moving and not bound, really bound in their valence bonds to metal very much. Okay, so let me show you this Java lab. Okay, I'm going to pull this up. So I just clicked on the link, and I'm at what the electroscope, and this is what the electroscope would look like. It'd have a large area right here where it's a flat area. It would look like kind of a pancake. Well, anyways, it would look like a large flat area, and then you have a metal rod right here, and then you have a hinge right here, and these two guys right here would be reacting to it. Okay, and so what happens is, here is your neutral object. Okay, and you're going to now, in this case, I'm going to bring an amber rod that I've rubbed amber against fur or plastic against wool, and now I've ripped those electrons off the wool or the fur, and they've gathered on the amber. So it's actually got a plus 1, 2, 3, 4, 5, 6. It's got an extra 7 electrons. Now here's the neutrally charged object, and here are the 2 plates. So if I bring this closer, notice those electrons are going to now flee that top plate, and they're showing that not all of them are fleeing. And since the electrons are gathering here at the bottom, okay, an excess of electrons are gathering here at the bottom, now they're repelling each other. And those two, that repulsion force is now making them, this plate, which was normally together, is actually going to drift and float in the air. So the more this bends away from this other one, the more electric charges, basically the stronger, more electrons that are gathered on this rod. Okay. Let's see what happens when we make this a positively charged object. It is possible to take positives off, to have a rod like glass. If you rub silk against glass, the silk, which is actually a little bit smoother than glass, is going to rip electrons off of the glass, and now that glass rod is going to be charged by an excess of charges. And in this case, again, this rod has lost 1, 2, 3, 4, 5, 6, 7 of its electrons, so now it's positive by 7. So when I bring this here close to it, what do you think is going to happen? Well, all the negatives are going to now try to gather as close to this rod as possible. So these negatives down here, this is a conductor, are going to now be attracted to that surface, and now it's going to be the positives that are repelling each other here. And this is a neutral dipole, this is a dipole here, so that's not responsible for it repelling. It's these 1, 2, 3, 4 protons that are repelling each other. Okay? So that's how charge polarization works, right? And that's how you could use an electroscope to actually measure how much charge is on a charged rod. If the electroscope barely floats up, I'm going to mark this document up. Hold on a second. Again, I'm going to mark the document up, so I'm going to hit comments, and this is going to pop out. I'm going to push it back in by hitting that arrow, and now I could use the pencil. Okay. So if those two pieces of tinfoil right here are just barely floating, okay, well, that may not be reacting, that's not reacting as much as those two pieces of tinfoil floating way out here, okay. Well, now it's really reactive. So whatever you're bringing close to this object, these two pieces are really repelling from each other. So it must be very polarized, okay. And so whatever object you bring close to it must have a lot of charge on it in comparison to this case, okay. So that's how an electroscope works, all right. And that's also how you could use an electroscope to measure how much charge is gathered on an object, and it's also an example of charge polarization. So in addition to charging by friction, you could, where you're ripping electrons off an object, or an object is having its electrons ripped off of it. So that's charging by friction. But there's also another thing called charging by induction, okay? And what you do is you use charge polarization, okay, to induce electrons to get close to the surface of that electroscope. And now what you do is you bring a neutrally charged object or a conductor close to it, and you could actually charge that neutrally charged object, or have that neutrally charged object give up its charge and add even more charge, negative charges to this object. So let's go ahead and try it out. Okay, so here let's describe what is happening here. So you have a positively charged object right here. Okay, and here you have, well, here you have a charged rod that is positive. You have a positively charged rod, and you bring it close to an electroscope, and you bring it close to a person, and the person is touching the electroscope. Well, if you bring this positively charged rod close to this electroscope, the electrons are going to come to the top, but most importantly, this neutrally charged person, their electrons are going to be towards the tip of their finger. And if they then touch the conductor, well, this person, who is also kind of slightly a conductor, is going to have his electrons pulled onto the surface of the conductor now. Okay, and then the person lets go. Well, now they've lost a bunch of electrons. Okay, and the number of electrons that would be is the deficit between this and this. So here it had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And this person over here now has 1, 2, 3, 4, 5, 6, 7, 8, 9. So they've lost 2 electrons. So they've lost these 2 electrons, and these 2 electrons are now gathered onto this surface, right? So now this neutrally charged electroscope now has an extra 2 electrons from the person. Well, now, since you've used polarization to pull those electrons off the person onto the electroscope, now the electroscope is in excess of negative charges. Well, now if you bring this rod away, now this electroscope is going to have an extra 2 electrons, and it's going to make those leaves permanently be repelling each other. Okay, so let me show you what I'm talking about by the simulation. Okay, I'm going to go back to this simulation, all right, and I'm going to do exactly what we did before. So here, the electroscope is neutral and the person is neutral. So if you touch it, nothing's happening, okay? But if the person brings their finger close to this, so the person is neutral again, and the electroscope is neutral. Again, if I bring the electroscope, this rod close enough, but not touching the electroscope is going to momentarily have its electrons brought to the surface, and these protons are going to now be repelling each other at the bottom, okay? And if I bring it back away, they'll go back to where they are. But here's what we're going to do. We're going to bring this guy close. So now it's drawn up the electrons from the bottom. And if I now touch it, this positively charged rod is actually going to pull electrons out of my hand, just like that. And now, if I remove my hand, and now if I remove this, those excess electrons are now going to result in a permanently charged, okay, an excess charge of negatives, and now those negatives are going to be repelling each other, okay? It looks like this is 5 and this is 5, and it's got a total of 6 there, so this has an extra 4 electrons on the bottom, okay? And so it's these extra 4 electrons, 2 here and 2 here, that are repelling each other, okay? There's another way you could charge by induction, and I could show it to you here. So I'm going to reset this little guy. And you're going to want to do it with a negative guy, okay? So let me show you the steps to that. For the other case, we were using a glass rod that had lost its electrons. Well, in this case, we're using an amber rod that has gained electrons from a wool shirt, or a plastic rod that has gained it from a wool shirt. Well, we're going to do the same steps. We're going to bring the electrons closer to this, okay? And now, when I bring my so again, this is a neutrally charged electroscope. My hand is neutral, so they're not doing anything. You don't see any electrons transferring from the objects, my hand or this electroscope. So I'm going to bring this guy closer. And notice the electrons again come to the bottom. Well, what do you think is going to happen when I touch my finger to this? Well, the excess electrons are going to actually momentarily jump off of this and jump onto me. Okay, now I'm going to remove my hand, and then I'm going to remove the rod. And now, since this is lost electrons, now it's going to be a net positively charged object. And now it's got an extra 1, 2, 3 protons that are unpaired with electrons. So these protons have lost their electrons. And now these guys are repelling each other, okay? So this is 2 ways that you could charge with induction, okay? So hopefully this is being informative for you. So both of these are dependent on polarization, and this is an electric force that comes out of this. And again, we're just going to call it an electric force right now, but in the next section, we're going to learn that this is actually called the Coulomb force. So when you bring a positively charged object close to this neutrally charged block, what's happening is the electrons are being attracted to these protons, and then these protons are being repelled away from this positively charged rod. And so since these protons are further away than these protons, that electric repulsive force is going to be small in comparison to these electrons being so close to these protons. And that's going to be a much larger force. So adding these 2 things up, by using vector addition, you get a net force up, okay? And that is the Coulomb force, and that's also called the electric force. And that's the reason why the negatively charged balloon will stick to a wall, because it's the opposite in this case. The electrons are down here, and those electrons are further away from the negative balloon, and the protons are now closer to the negative balloon, and even though they're just infinitesimally closer, it creates a much larger force. Okay, so there's some kind of distance relationship to this attractive repulsive force. So just to reiterate, that electric force comes from that repulsion between like charges. So if you have two like charges, two positives or two negatives, they're going to repel. However, if you have unlike charges, a positive and a negative, well, they're going to attract. Okay, so that's basically a rule. And so how do you go about figuring out if an object, what charge an object is? Okay, well, if you bring an object close to another object and there's no reaction between the two, you could assume both of those are neutral in charge. However, if you bring an object closer to another object and they're repelling, okay, then you know those are like charges. They're either both positives or both negatives. And since this is plastic, it's mostly, you're probably going to think that this plastic is mostly, it's got an excess of negatives on it, right? Well, if this had only 3 electrons built up on it, 3 on each, so there are 3, well, let me rewrite that again a little bit more. And I'll use blue to represent electrons, because for some reason I think of blue when I think of electrons. So this has 3 electrons built up on it. So these 3 are reacting to these 3. Well, if you bring these two objects, which are opposing each other, close to each other, and this distance is important. Here they're only a very small distance away from each other. But if both objects, or one of the objects, had even more electrons built up on it, then the distance would be even more increased. So the more charges must mean that there are more electrons on it. So the more electrons on it, can be more of a repulsive force. So distance is important, but also the number of charges. All right. If you have glass rubbed with silk, well, again, I kind of mentioned this earlier. Silk is more smooth than glass. Sounds weird, but it is true. And so that means the silk, when you rub neutrally charged silk with glass, the glass is more rough, so it's going to give its electrons to the silk, and now the glass is going to be positively charged. Okay. Okay. And so that is going to result in a repulsive force too. Again, the more charges, the larger the repulsive force, so that means the distance is going to be increased. The separation distance between that repulsion is going to be increased. Conversely, again, you have glass rubbed with silk. You could expect that that's going to have, it's going to have lost its electrons. And plastic rubbed with wool, it's going to have gained electrons from the wool. So now, this plastic rod is now going to be attracted. And again, the more charges built up on it, the more attracted that they're going to be. Okay, so that means this distance is going to be even closer. So that separation distance is going to be even stronger. So closer, so when attraction comes into place, that means there forces, that attraction force is even going to be stronger. Okay. While if it doesn't have as many negatives or positives built up on it, it's going to not be as close. Okay. And the interesting thing too is that when you have rubbed the wool against the piece of plastic, now the wool is going to have an excess of charge, and it's actually going to be attracted to that negatively charged piece of plastic that it gave its electrons to. So they'll be attracted to. Pretty cool. So now that you've gone through all of that, what I want you to do is I want you to try the lecture tutorials, lecture 1, and this is charging by induction, and then also using the electroscope. And don't forget, you've got this simulation that I want you to actually use, and I put that link earlier when we were talking about electroscopes. So I want you to go ahead and try those out, and then in our WebEx, we'll go ahead and talk about these two problems, okay? So I hope you enjoyed this lecture, okay? And we're going to move on in the next lecture to the Coulomb force and also Coulomb force in one dimension. So brush up on your force diagrams, okay? Thank you very much. Bye.